Hello, I'm going to talk a bit about Babylonian mathematics, which is some of the most fascinating mathematics from the ancient world. And when I say ancient, I mean seriously ancient, so nearly 4,000 years old. Pythagoras, who was one of the earliest of the ancient Greeks, wasn't born until about 500 BC, and that's only 2,500 years ago. And the Babylonians achieved a level of sophistication that Pythagoras could only dream of, really. So that's my title. I'm going to talk about this artifact towards the end of the video, which is really the jewel in the crown of Babylonian mathematics. So, Babylon. If you lived 250 years ago, you could be forgiven for thinking that Babylon was a myth. Very little was known about it. It wasn't even known where it was. And then at the beginning of the 19th century, it was rediscovered, and here it is in the middle of Mesopotamia, between the Euphrates and the Tigris. Well, on the Euphrates, actually. It's been excavated extensively since then. And as well as uncovering the city, masses and masses and masses of written material has been excavated. And it's now been interpreted. So now we know a great deal about Babylon and about Babylonia, and this is one of the empires that was centered on Babylon. So Babylon was at its height from about 2000 BC to about 200 BC. Well, actually, it was at its house twice, really. Twice it was probably the largest city in the world and the center of a large empire, roughly 1,000 years apart, as you see here. And this is what Babylon looked like in the Second Empire. Isn't that fantastic? So that is a reconstruction of the Ishtar Gate, named after the great goddess Ishtar. It was originally built by Nebuchadnezzar at the height of the Second Empire. Most of the mathematics we deal with, though, comes from the First Empire. All the writing is in cuneiform, which was the oldest form of writing in the world, goes back even further than Babylon. It was used for over 12 languages, so it's a script, not a language. And then it was lost and forgotten for, 2,000 years, really, until, again in the 19th century, it was rediscovered and deciphered. And this is the key to deciphering. You might think of it as the Rosetta Stone of cuneiform, because this is a proclamation by King Xerxes in 3 different languages, all of them in cuneiform. How many tablets survive? There's an estimate somewhere between 500,000 and 2 million of these clay tablets have been excavated and sitting in the basements of museums around the world. Only about 100,000 of them so far been read, so there's masses more to discover. This is what cuneiform looks like. So it's mostly written on clay, damp clay. You poke a sort of stylus into it to make these marks. It's a wonderful material, of course, because if you want to reuse it, you just sort of roll it up, smooth it out, and perhaps redampen it a little, and then you can use it again. But if you want to keep it as you would if you were an accountant keeping the king's records, you fire it. And that turns it into a brick, essentially, and then it will last forever. At least it will in the right climatic conditions. It turns out that those are not present in Babylon itself. It's too close to the Euphrates, which has flooded it and inundated it several times over the thousands of years. And that's really not an ideal way to keep records. So almost all the tablets that we found are from elsewhere in the Babylonian Empire. These groupings of symbols represent either words or syllables. And it turns out that of those 12 languages that were written in cuneiform, some of them have descendant languages that are still spoken today. And so for the syllables, we can have a fair shot at working out how they were pronounced, which leaves us in the rather curious position. There are some words in ancient languages that we know how to pronounce, but we don't know what they mean. Well, there we go. So anyway, it's the numbers we're interested in. So here are the numbers. At first, they look a bit like Roman numerals, don't they? Except with no V's and L's. So these are the 1s, 2, 3, 4. So you have up to 9 of those. And this is the symbol for 10. You have up to 5 of those. But no, you don't go any further than 59, because this is really a base 60 system. So it's best to think of one of these combined symbols here as a single digit base 60. So this is the digit 36, and that's the digit 14. And then after 59, we get to, we would have sort of 1 0, wouldn't we? 1 times 60 plus 0, but they didn't have a 0. So let's see how that works. Right, now we're going to have a mixture of decimals and sexagesimals in what follows. So I'm going, from now on, I'm using black for sexagesimal and blue for decimal. So when we write 2, 3, we mean 2 lots of 10 plus 3, or what we call 23. And in a similar sort of way, when the Babylonians wrote 2, 30, they meant 2 lots of 60 plus 30, which is what we'd call 150. So far, so familiar. Now, they didn't have a 0, though. You probably noticed there wasn't a 0 on that previous slide. So 230 can also mean, as it were, 230, which would be 2 lots of 60 squared, 30 lots of 60 and nothing more, which is 9,000. Now, what you read is that if it's not clear from the context which is meant, you have to say that in the words. You'd think that would be a bit of a disadvantage, really. Like if you're the king's accountant, you'd want to know whether this guy that you were taxing had 150 cows or 9,000. But it turns out mathematically it's really quite convenient that you can treat these as exactly the same number. It opens up some really interesting possibilities. Well, as well as using them for integers, they used sexagesimal for fractions. So this number can also mean, as it were, 2.30, which is 2 units, and 30 lots for 60th, which is what we call 2.5 or 2.5. Or, of course, we could go one further to the right, and that would be, as it were, 0.230, which is 2 over 60 plus 30 over 60 squared, which is what we'd call a 24th, or 0.416 recurring. A 0 in the middle of where we'd want a 0 in the middle of a number, this left a gap. So this thing here is 2 lots of 60 squared plus 30, which is 7,230. That is a cause of occasional error, as you can imagine. Okay, and in fact, right towards the end of the Babylonian period, they did invent a sort of 0 to put in a gap like that, but they never used it at the end of a number or at the beginning. Now, it turns out that a surprising number of the tablets that have survived is our school exercise books, basically. In fact, I believe there is one where the teacher has marked the student's work. I haven't been able to find that, but so the pain of marking homework goes back nearly 4,000 years. So here's an example. Here's this kid's 10 times table. Even in sexagesimal, a 10 times table is pretty simple, actually, but it's worth it looking at. So let's look at it. So this says 10 times 1 is 10. That's the symbol for multiplication or times. Times 2 is 20. Times 3 is 30. 40, 50. Times 6 is 60. Now, that really does look exactly like 1, doesn't it? But the context makes it clear. You know that means 60, not 1. Times 7 is 70, and so on, up to times 12 is 120. So that's the 10 times table. But of course, this symbol here, as well as meaning 10, could also mean, as it were, 0.10, which is a sixth. So this is also a 1/6 times table, in which case this really is 1, of course. 1/6 times 6 is 1. It's also, therefore, a dividing by 6 table. So if you know how to multiply by 10, then you also know how to divide by 6. Same method, same thing, you just multiply by 10. That is dividing by 6. So that's really quite cool. Let's look at the back of the table. This carries on up to times 20 is 200. That's 180. Sorry, this one, isn't it? 20 is 200, 180 plus 20. So that's 10 times 20 is 200. And then 30, 40, and 50. So it turns out, there are lots and lots of these multiplication tables being excavated. They all do the same thing. It's up to 1 to 20 and then 30, 40, and 50. The other number, the analog of 10 here, is very varied. There are up to 50, I believe, different numbers have been found to have multiplication tables, including 72, which is quite a nice one, or 1 on the 5th, depending on which you think of it as. And the scribes learnt all these, or at least not necessarily all of them, a great many of them. So clay tablets are quite heavy, so you don't want to have to carry them around like log tables, as it were. You need to memorize them. So they remember a huge number of multiplication tables. Right, now, so we've seen this relationship between 10 and 60. They're very interested in regular numbers. Well, we call them regular on their behalf. What we mean by that is numbers whose only prime factors are 2, 3, and 5. And they're the ones, if you think about it, whose reciprocal, so 1 over that number, will have a sexagesimal fraction terminates. So in our decimal system, the corresponding idea is numbers whose prime factors are only 2 and 5, and they're the ones with terminating decimal fractions. So here they are. These are the first few, what we'd call regular decimal numbers, and those are their reciprocals. Here it is in Sexagesimal. And again, many copies of this table have been recovered. And it's the same sort of thing in Sexagesimal. So this is to 30. So that says 1 over 2 is 30. Well, it's not 0.30, but it's just 30. A third is 20, a quarter is 15. And here's the one we've just been looking at. 1 over 10 is 6, or 1 over 6 is 10. So this is all the regular numbers up to 81. That's 81. And their reciprocals. So the scribes all learnt this table, and they probably learned all these multiplication tables, and so they knew how to divide by a lot of numbers as well. So let's just try our hand at Babylonian arithmetic. We don't know quite how they did their arithmetic. They almost certainly didn't do it in writing. That's a relatively modern idea. Until relatively modern times, people always did their arithmetics on abacus or counting board or something. So I expect that was the Babylonians did as well, but we don't know. But supposing you did do it in writing, well, you can do addition, can't you? So 45 and 32, that's 77, that's 17, remainder 1. There's a 0 here because there's a digit missing, but that's okay. 15 plus 1 is 16, and so on. So addition's easy, really. Abstraction's not much more difficult. Number 1s to 60, a useful thing to know, aren't they? I bet they learnt those as well. Actually, they're particularly easy in Sexagesimal, aren't they? Because 17 has 1 in the tens, 1 10 symbol, and 7 1. So you can almost visually see what the number bond 60 is, that it's going to be 43. So 43 plus 5 is 48. Carry 1, there you get. There you go. So subtraction is easy enough. Now I said mostly they did division by multiplication, but actually very small numbers you can divide by relatively easy, just the same as we do. So take this number and divide it by 2. So 2 into 1 won't go. Carry that. 124, that's 84. Half of that is 42. 2 into 51 is 25, remainder 1. 110 is 17. Half of that's 35. So that's half of that number. Okay, now then, here's the thing. This number we just looked at is in fact the Babylonian commonly used value for root 2, which as a decimal is this, and the real value of root 2 is this. So it's correct to 5 decimal places. It's pretty impressive, and that's the ratio between this approximation and the real thing. That's pretty amazing. So now let's look at an example of all this. So this is another clay tablet, again, First Empire. And what is it? Well, it's a square with diagonals, isn't it? What else can we say about it? Well, so this is that Babylonian version of root 2. This is a half, and this is a half of root 2. So this is a square of side 30 with diagonal half of root 2. This is what's called a handheld tablet. So it's a small round blob of clay, which you sort of paper, and then you show the teacher. It's a sort of mini whiteboard of Babylonian times. How did they work out their square roots? Well, they use the Newton-Raphson method, of course. So to find the square root of a number k, it's an iterative method. You make a guess, and then you make this calculation. You take your guess, add it to the number you're trying to find the square root divided by your guess, and halve that sum, and that's your next guess. So this was later ascribed to this ancient Greek, or this slightly less ancient Greek, or even Newton. Well, I dare say Newton was quite proud of making his discovering his method, but the Babylonian scribes had been using it 3,000 years earlier. Well, of course, Newton and Raphson is more general than this. I think the Babylonians only use it for square roots, as far as I'm aware. Right. So actually, the calculation is quite easy. Let's do it. So first approximation is 1. So now we do this thing. We take 1 plus 2 divided by 1. Divide that by 2. That you can do that in your head. That's 3 over 2, which is 130, what we call 1.5. Next we take this guess, divide 2 by that guess, add them and divide by 2. Well, that's a regular number, so you can do that one in your head, and that's 120. So that's 250 divided by 2, which is 125, which is that. That's already getting quite close. The final stage is a bit more difficult. So this plus 2 divided by that. Now this number is not a regular number, so you have to do some hard work to divide by this. But you don't have to do it once, because then you write the answer down, and Babylonian scribes will forever know what value to use for root 2, and they did. They probably all knew this. What else could they do? Well, one of the things they could do is solve quadratic equations. And how did they do that? Well, they knew the formula, of course. 4,000 years ago, they knew the quadratic formula. Of course they did. So actually, there were three sorts of quadratic equations as far as they are concerned, because they didn't have negative numbers. So these are three apparently different, well, certainly different looking quadratic equations. And for the Babylonians, they would actually have been different sorts of equation. But they knew how to solve all three. The fourth sort, actually, you can't even express without negative number or zero. And it's only got negative solutions anyway, so basically that one didn't exist. But they solved this using essentially the quadratic formula. There are lots of examples of scribes writing down how to solve equations like this. And what you do is you start by halving this number, and then you plug it into this formula, and that is the quadratic formula. And the other two versions have the same thing. And of course, we know that they know how to do square roots, so they can solve these things. Actually, the method for solving non-monic polynomial quadratics, i.e., where this coefficient isn't 1, is really cute. Again, it's showing how to do this. So you multiply the whole equation by a and get this thing, and that's now a monic equation in ax squared plus p times ax equals this aq thing. So you solve that for x using this method and then divide by a. Cute, isn't it? I use that method now. Okay, so they had a method. What they didn't have was a formula. So I said they knew the quadratic formula. They didn't know it as a formula. Of course, they couldn't have a formula in quite our sense of the word, because they didn't have any letters. Cuneiform has words and syllables. They don't have letters. So they couldn't do it quite the way we do it. And they didn't actually do it all that much like the way we did it. They knew the method. And there are lots of descriptions of using the method, but they're all for particular equations. So the idea is you watch somebody solving x squared plus 7x equals 2, whatever it is, and then doing another one, and perhaps another one, and you've got that, and then you know the method, but you don't actually know a formula. Okay. Right, now we're going to move on to that wonderful artifact. And to do that, we need to know about Pythagorean triples, because this thing is all about Pythagorean triples, 1,300 years before Pythagoras was born. So a Pythagorean triple consists of three numbers, a, b, c, such that a squared plus b squared equals c squared. So geometrically, c is the hypotenuse of a right-angled triangle, and these are the other two sides. But we don't need to have triangles involved, really. We can just think about numbers. So these are three quite small Pythagorean triples, and here's a really enormous one. There are infinitely many of them, of course. The other thing we need to know about is a Pythagorean triple is called primitive if a, b, and c have no common factor. So they're not all even, for example. They're not all divisible by 3. So 6, 8, 10 is a Pythagorean triple. It's just double this one. So the triangle is the same shape, if you like. So it's not terribly interesting. And we're really only interested in primitive Pythagorean triples. Okay, now let's look at this thing. From Babylonia, southern Babylonia, actually, apparently you can tell that because the handwriting is the style of southern Babylonia. About 1800 BC, the First Empire again. And it's all about Pythagorean triples. So let's have a closer look. What is it? Well, it's clearly a spreadsheet, columns of numbers, a heading which tells you what those columns are, and you can see the row number 1, 2, 3, 4, 10, 11, 12, 13. Right, so it's a spreadsheet. So a lot of effort's been put into reading this, so we know what it says now. So here it is. Now then, what is all this? So it turns out these are two of the two parts of a Pythagorean triple. The heading says this is the width and this is the diagonal. So that looks like a triangle. It looks like a rectangle, actually, doesn't it? So it's two triangles stuck together. But anyway, that's the diagonal, that's the width. And so the third side would be the length. This is actually not what it says to the column of this heading. We'll come to that. But that's what it is. So these are two elements of the Pythagorean triple and this amazing calculation, which is the width squared divided by the length squared. Well, that's fairly astonishing. The amazing thing is these are exact sexagesimal fractions. So Of course, we don't know where the sexagesimal point is, as it were, but these are integers, and this is a number just less than 1, isn't it? Very nearly 1 in this case. It's 0.59, down to about a third. So that in the order of this column, and these are exact fractions, which means that the length is a regular number, because the length square has got to be a regular number. So what these are then is a set of Pythagorean triples for which the length is a regular number, and they're ordered in this way. So how would you do that? Oh, and of course the width is less than the length. The length is the longer of the two sides. And by the way, there's some pretty big numbers here. Look at this one here. Actually, that in decimal is that. That's that enormous one I showed you before. There are lots of smaller Pythagorean triples than that. So what's going on here? Well, this is pretty constraining to make the length a regular number. So let's see. So let's just have a look at what this column actually says, because that's interesting. So here's our Pythagorean rectangle or possibly triangle. And that first column is, in fact, width squared divided by length squared. So it's that area divided by that area. And well, that's if you know that this area plus this area is equal to that area, looking at the ratio of these two areas is an obviously interesting thing to do. Well, that's what we'd call tan squared of A, isn't it? That squared divided by that squared. But they didn't have angles, so they certainly didn't have trigonometry. So that's definitely not what they were thinking. But they must be getting quite close. Okay, so what does the column heading actually say? It says it's the tangletum of the diagonal from which one is torn out, so that the width comes up. Well, now, what do we make of that? So comes up is the phrase that's usually used just to mean it's the answer. So, that's the result. Tangletum is, unfortunately, one of these words that we know how to pronounce. We don't know what it means quite. And one's been torn out from it, which presumably means one subtracted from it. So presumably the tangletum of the diagonal would be diagonal squared of a length squared. That's sec squared of A for us. And take 1 from that and you get tan squared of A. So that's amazing, isn't it? So I suppose this is the tangletum of the diagonal from which one is torn, so that the tangletum of the width comes up. Maybe that's what's really meant. Who knows? Anyway, that's all very interesting. The question is, how would you generate this sort of thing? Well, we know how to generate Pythagorean triples. At least we do if we've had a university mathematical education. This is not taught in schools, but you can generate Pythagorean triples by taking any two numbers, which are integers, positive integers, which are coprime and not both odd, and you perform this calculation with them, and it turns out these are a Pythagorean triple. That squared plus that squared equals that squared. More remarkably, it turns out all Pythagorean triples can be made that way. And so long as m and n are coprime and not both odd, then this is a primitive Pythagorean triple. Now we want, it also turns out that either of these can be a little bigger than the other, depending on the m and n. So if m and n are quite similar in size, this is quite small, and this is the bigger side. Whereas if n is a lot bigger than m, then this is the bigger side and this is the smaller side. It's obviously quite easy to make this number regular because you've just got to choose m and n to be regular, and then that will be regular. So what we want to do is generate Pythagorean triples by choosing coprime regular numbers, m and n, so that n is not too much bigger than m, so that this is the bigger, so this is the length and that smaller number is the width. Oh, well, how would you do that? Well, you would do it on a spreadsheet, wouldn't you? So here we are. Here's my spreadsheet. So this is m, the numbers. So I've chosen my regular numbers less than 60. It goes up to 54. And for each of those, I've chosen all the possible n's that are bigger than this, but not too much bigger. Turns out this formula here tells you how much bigger you can afford to be. So there we are. Turns out there are 38 such pairs. And then you calculate A, B, and C. This is the one that isn't on the Plimpton thing, but it is the bigger side. This is the hypotenuse, and this is the tangletum. Good. Right, so now what you want to do is sort them into decreasing order of tangletum, don't you? So let's do that. There we go. Turns out these first 15 rows of this are the 15 rows of Plimpton. Amazing. Well, almost. There's some slight differences, which we'll come to, but pretty much this is the first 15 rows of Plimpton. So that very complicated calculation I've done comes up with pretty much exactly Plimpton 322. So I think that's pretty good evidence that that is precisely how they calculated it. That is pretty amazing. Now, I said it's not exactly right. Let's just see. It's quite revealing what's gone on here. So the first difference is on row 11, which is what we'd call the 3, 4, 5 triangle. So I mean, it's actually the first row in my spreadsheet before I sorted it. It's 3, 4, 5 triangle. So what it says on Plimpton 322 in these two rows is 45 and 115, which is by no means primitive. In fact, it's 15 times as big as 3 and 5. Well, it just turns out that, of course, the 3, 4, 5 triangle is a very familiar object to us and to the Babylonian scribes, and they always referred to it as the 145, 115 triangle, meaning, I think, 1 3/4, 5/4. But whichever version they meant, that's just their favourite name for it. So that's why that one's not primitive. The other one's more interesting in a way. So it said you have to choose M&N that are not both odd. But if you do choose odd ones, you still get a Pythagorean triple, but it's not primitive. In fact, here we are. All those numbers are divisible by 2. They're always divisible by 2 if you use 2 odd numbers. Let's convert those into sexagesimal. So what it says on Plimpton is that. So what you do, having generated this, is divide all these numbers by 2, wouldn't you, and get a primitive one, because then you've got smaller numbers to work with to calculate the Tackleton. Well, what you've written is this and that, so that's half that. So it looks as though he halved that, but forgot half that. But nevertheless, the Tackleton's correct. So if you use either this pair or that pair, you'll get the same Tackleton, of course, and that's the one you get. That's one that's there. So it's just a copying error. The next one is a mystery, really. Who knows what's going on here? So that's what it says on my spreadsheet. This is sexagesimal version of that, and this is what it says on the Plimpton. So this one's correct. This one isn't. There are all sorts of fanciful explanations for where this number comes from, but none of them is entirely satisfactory. It's possible he just had a brainstorm, has copied something down from somewhere completely different. I mean, he'd have intermediate results on various other tablets, probably, wouldn't he? So he just copied the wrong one, perhaps. Who knows? Either way, the Tackleton is correct, apart from a little typo. So, well, not a typo, a wedjo, I suppose. Anyway, so he should have, in that long string of sexagesimal digits in the fraction, it should have had a 50 and then a 6, and he's got a 56 instead. But it's otherwise correct. So this is a spurious. It's just a copying error again of some sort. Okay, so now we know pretty much how it was calculated. Well, the next question is why? Again, nobody really knows. Is it just a sort of exercise? It's a jolly complicated exercise, isn't it? There's a hint come up. So relatively recently, this tablet has been read. So I said there are only a very small fraction of tablets that have been read, and this is one read quite recently. It's been hiding in plain sight in a museum in Turkey for 100 years. Again, it's roughly contemporary with Plimpton 322, old First Empire. And what is it? Well, you can see on this side is a bit of geometry. On the back side, there's a story. It's all about resolving a land dispute. So a piece of land was divided in two between two people, and the dispute arose about who owned the palm trees near the border, whether his side of the border or my side. So the local administrator sent a scribe out to sort this out, and what the scribe did was divide the land area into Pythagorean rectangles and Pythagorean triangles. He really did. And that's how he got hold of a firm idea of where the border was and where which side of the border the palm trees were. I think that's extraordinary. So it turns out that perhaps having a table of Pythagorean rectangles or triangles of varying shapes would be a handy thing to have. And so maybe that's what Plimpton 322 was about. And maybe it's not trigonometry because they didn't measure angles, but maybe what they did in situations where we might want to measure an angle, what they perhaps did was to fit a Pythagorean triangle into the angle, as it were, the closest one they could find, and then you do their calculations based on that. So they could, as it were, go straight to the what we'd call trigonometric ratios without actually having to measure an angle. So there we go. It's very interesting, isn't it? So that's a little taste of Babylonian mathematics. I hope you enjoyed it.